A spiral galaxy hangs in the void, a majestic pinwheel of stars and light. But what if everything we know about how galaxies work is wrong? Astronomers have found a galaxy that breaks the rules, a cosmic rebel called NGC 1052 DF2. This strange collection of stars appears to have no dark matter, the invisible glue that holds the universe together. Its existence defies the laws of physics as we understand them. By the end of this journey, you will understand the high stakes of a discovery that could rewrite our cosmic rulebook. We will follow the astronomers who found it, dive into the fierce debate that split the scientific community, and uncover what this means for the fate of everything. How do you even weigh something you cannot see? And what happens if the foundation of modern cosmology is built on a mistake? This is a detective story written in starlight. What do you think is more likely, that we have misunderstood gravity, or that the universe is hiding an entirely new kind of object? The entire universe is held together by a ghost. For nearly a century, astronomers have known our cosmic maps are incomplete. The stars we see, the galaxies we photograph, they account for only a tiny fraction of what must be there. The rest is dark matter. Think of it as the invisible framework, the cosmic scaffolding upon which the bright universe is built. Without it, everything we observe would simply fly apart. But how do you prove the existence of something you cannot see, touch, or directly detect? You look for its shadow. The first major clue came from the way galaxies spin. In a spiral galaxy like our own Milky Way, stars orbit the center. According to the laws of gravity, stars on the outer edges, farther from the galactic core, should move more slowly, just as Pluto orbits our Sun much more sluggishly than Mercury. But when astronomers measured these rotations, they found something shocking. The outer stars were whipping around just as fast as the inner ones. It was as if the entire galaxy was spinning like a solid plate, a violation of Newton's laws. The only explanation was that each galaxy was embedded in a vast, massive halo of something invisible, its gravity pulling on those outer stars, speeding them up. That something is dark matter. Another line of evidence comes from gravity's magnifying glass. Massive objects warp the fabric of space-time, bending the path of light. This effect, called gravitational lensing, allows us to see distant galaxies distorted into arcs and rings. By studying these cosmic mirages, scientists can map the distribution of mass in the universe. Time and again, these maps reveal far more mass than the visible stars and gas can account for. The lens is being bent by the gravity of the unseen. Finally, the echo of the Big Bang itself, the cosmic microwave background radiation, carries an imprint of the early universe. The precise patterns in this ancient light tell us how much ordinary matter and how much dark matter existed when the cosmos was just an infant. The math is unequivocal. Dark matter is not a minor component. It outweighs all the stars, planets, and interstellar dust by a factor of 5 to 1. It is the dominant form of matter in the cosmos, the unseen architect of the cosmic web. So when a galaxy is found that seems to lack this fundamental ingredient, it is not just a curiosity, it is a direct challenge to the blueprint of the universe. How could a structure be built without its scaffolding? This ghostly galaxy was spotted by a telescope built to see the invisible. Astronomer Pieter van Dokkum and his team were not using a traditional giant mirror. They were using the Dragonfly telephoto array, a cluster of ordinary camera lenses engineered to reject scattered light. Its specialty is finding the faintest, most diffuse objects in the sky, the cosmic whispers everyone else misses. And in 2018, it found a whisper that would shout. The galaxy was catalogued as NGC 1052 DF2. It was a member of a strange class called ultra-diffuse galaxies. Picture a ghost of a galaxy. It is physically as wide as our Milky Way, a sprawling cloud of space, but within that vast volume, it holds only about 1% of the stars. Its stars are so spread out you can practically see right through it, a wispy, ethereal cobweb against the dark. The initial observations were puzzling enough. But the real mystery began when Van Dokkum's team pointed the mighty Keck telescope in Hawaii at its individual stars. They measured the motions of 10 bright star clusters within the galaxy. In a normal galaxy anchored by dark matter, these clusters would be orbiting at high speeds, tugged by the powerful gravity of all that unseen mass. But the measurements from Keck told a different story. The clusters were barely moving. They were drifting slowly like lazy boats on a calm pond. This was the first stunning clue. The galaxy seemed weightless. If there was no extra mass holding it together, then the visible stars themselves must account for all the gravity. And when they did the math, the numbers matched perfectly. The motion they saw could be explained by the gravity of the stars alone. There was no room left for dark matter. The scaffolding was missing and the building was still standing. How could such a fragile thing even exist? The key to this cosmic mystery was not in seeing the galaxy's mass, but in hearing its rhythm. To weigh something invisible, astronomers turned to the galaxy's natural speedometers, ancient objects called globular clusters. Imagine dense, shimmering balls of hundreds of thousands of stars, each cluster a miniature city of suns. They orbit far out in the galactic suburbs, tracing wide paths around the galaxy's center. Their speed is the telltale clue. Picture swinging a ball on a string around your head. The faster you want that ball to spin, the harder you have to pull on the string. That pull is gravity, and the strength of that gravity depends on how much mass is inside the ball's orbit. In a galaxy, if the globular clusters are zipping around at incredible speeds, it means there is a tremendous amount of mass pulling on them, most of it the unseen dark matter halo. If they are drifting slowly, it suggests the galaxy is lightweight, held together only by the gravity of the visible stars you can count. Pieter Van Dokkum's team pointed the Keck Observatory, one of the world's most powerful telescopes, at the 10 brightest globular clusters in NGC 1052 DF2. They expected to measure the high-speed blur of stars caught in a powerful dark matter grip. They meticulously recorded the subtle red and blue shifts in the cluster's light, the fingerprint of their motion. The data came in. The clusters were not racing, they were meandering. Their measured speeds were so low they could be explained entirely by the gentle tug of the galaxy's sparse, visible stars. The math was stark and simple. For the first time, it appeared astronomers had found a galaxy where the dark matter scaffolding was completely absent. This was not a measurement error or a trick of the light. It was a direct, observational challenge to a fundamental rule of the cosmos. The numbers told a story that defied belief. When the team calculated the total mass of the galaxy based on the languid motion of those globular clusters, they arrived at a figure of around 200 million times the mass of our Sun. Then they independently calculated the mass contained in all the visible stars, gas, and dust they could see. That number was almost identical. For the first time ever, the two measurements lined up. There was no missing mass, there was no hidden component. The galaxy's gravity came solely from the stuff you could point a telescope at. In NGC 1052 DF2, the dark matter was simply not there. This was the bombshell. In every other galaxy ever studied, from majestic spirals to tiny dwarfs, the mass inferred from motion was always 5, 10, even 30 times greater than the mass of the visible material. That gap was the signature of dark matter. Here, the gap was zero. The result was so clean, so stark, it felt like finding a skyscraper standing tall without any steel frame, held up by its bricks alone. It was a direct challenge to a universal rule, a single, silent exception that demanded an explanation. If this galaxy was real, what did it mean for everything else? A discovery that shatters a fundamental rule is met not with celebration, but with intense scrutiny. The astronomical community's immediate reaction to NGC 1052 DF2 was a wave of profound skepticism. Could a galaxy truly exist without dark matter, or was this a case of mistaken measurements? The entire shocking conclusion rested on one critical number: the distance to the galaxy. Get that distance wrong and the entire house of cards collapses. Here is why. The method for weighing the galaxy relies on comparing observed motion to physical size. Think of watching a car drive past in the distance. If you misjudge how far away it is, you will also misjudge its speed. A car that is actually very far away and moving very fast can appear to be close and moving slowly. The same principle applies to galaxies. The team calculated the galaxy's mass using the measured speeds of its globular clusters and the galaxy's apparent size on the sky. But to turn that apparent size into a true physical size, you need to know the distance. If the galaxy was much closer than they thought, its true physical size would be smaller. A smaller galaxy with the same observed star speeds would require much less total mass to hold it together. In other words, a miscalculated distance could make a perfectly normal, dark matter-rich galaxy look like a ghostly anomaly. This distance debate became the first major battlefield. Rival teams pointed the Hubble Space Telescope at NGC 1052 DF2, using its sharp vision to study individual, aging red giant stars within it. These stars have a known intrinsic brightness acting as standard candles. By measuring how dim they appear from Earth, you can calculate their distance. The results were conflicting. Some analyses suggested the galaxy was indeed about 65 million light-years away, as Van Dokkum's team claimed. Others argued it was significantly closer. A difference of just 10 million light-years in either direction was enough to swing the mass calculation from revolutionary to ordinary. For a time, the fate of the dark matter-free galaxy hung on this single, contentious number, a testament to how one elusive detail can hold an entire cosmic mystery in the balance. The galaxy's fate rested on a single, fundamental measurement: how far away it truly was. To understand the fierce debate, you need to grasp the cosmic yardsticks astronomers use. One of the most reliable is the red giant branch star. In the final stages of a star's life, it swells into a red giant, and for a specific class of these aging stars, their intrinsic brightness is remarkably consistent. They are like standard light bulbs scattered across the universe. By measuring how dim such a star appears in a distant galaxy, astronomers can calculate its distance. Pieter Van Dokkum's team used this method with Hubble data, placing NGC 1052 DF2 roughly 65 million light-years away. At that vast distance, its large physical size combined with the slow star motions demanded a shocking conclusion: a galaxy with no dark matter. But another team, led by Ignacio Trujillo, looked at the same Hubble images and saw something different. They focused on a different kind of object: planetary nebulae. These are glowing shells of gas ejected by dying stars, and their brightness can also serve as a distance marker. Their analysis suggested the galaxy was much closer, perhaps only 42 million light-years away. This difference of 23 million light-years is not a small error, it is a cosmic game-changer. Here is why distance is the linchpin. Think of watching a spinning figure skater on a screen. If you are told she is far away, you interpret her size as large and her spin as gracefully slow. If you learn she is actually much closer, your brain recalculates she is smaller and spinning wildly fast. Apply this to the galaxy. A closer distance means its true physical size is smaller. A smaller galaxy with the same observed star speeds requires much less total mass to explain those motions. Suddenly, the mass calculation shifts. The galaxy could be an ordinary, faint dwarf galaxy, its motions perfectly explained by a normal amount of dark matter. The revolutionary anomaly would vanish into a simple miscalibration. For years, the scientific community watched this tug of war. Knowing the answer to the universe's greatest ghost story depended on who was right about a number. Then came a second ghost. Just as the debate over distance raged, Pieter van Dokkum's team made another discovery in the same patch of sky, a galaxy catalogued as NGC 1052 DF4. It was another ultra-diffuse wisp, another cosmic cobweb, and when they pointed their telescopes at its star clusters, they measured the same eerily slow motion. The data told the same impossible story. This galaxy, too, appeared to have no dark matter. One anomaly could be dismissed as a fluke, a cosmic oddball, or a measurement error. But two of them, found in the same galactic neighborhood, that changes everything. It suggests a pattern. It hints at a process. Suddenly, the conversation shifted from "is this one galaxy real?" to what could create galaxies like this. Finding a second example was the crucial plot twist in the mystery. It moved the question from the realm of possible mistake into the realm of genuine phenomenon. Scientists now had to confront the idea that these were not errors but evidence. They were looking at a new class of object, galaxies built without the universe's primary construction material. The search for an explanation became even more urgent because if it happened twice, it could happen many times. What cosmic event could strip a galaxy of its ghostly essence, leaving behind only the faint, visible bones? The discovery of a second ghostly galaxy demanded a natural explanation, one that did not require rewriting the laws of physics. For the skeptics, a compelling answer already existed, written in the language of gravity and violence. The leading theory is called tidal stripping, and it paints a dramatic picture of cosmic theft. Both NGC 1052 DF2 and its sibling are not floating in isolation. They are found orbiting a monstrously large elliptical galaxy known as NGC 1052. This giant neighbor is the key to the entire mystery. Imagine a dense, powerful magnet moving through a cloud of iron filings. The magnet's gravity pulls most strongly on the filings closest to it, yanking them away. Now replace the magnet with a giant galaxy, and replace the iron filings with the dark matter halo of a smaller, passing galaxy. This is tidal stripping. Dark matter, unlike stars, does not clump in a tight central core. It forms a vast, diffuse sphere that extends far beyond a galaxy's visible edge. Because it is so spread out, it is incredibly vulnerable to gravitational tides. When a small galaxy ventures too close to a giant, the difference in gravitational pull between the side nearest the giant and the side farthest away creates a stretching force. This tidal force acts like a cosmic thief, preferentially peeling away the loosely bound dark matter from the outskirts of the smaller galaxy. Sophisticated computer simulations show this process in stunning detail. You can watch as a dwarf galaxy, initially rich with dark matter, swings past a larger companion. Long, faint streams of dark matter are siphoned away, drawn out into great arcs that vanish into the void. What remains is the galaxy's dense, compact heart of stars, which are much harder to pull apart. The result is a ghost, a galaxy that looks for all the world like it formed without dark matter, when in reality it was brutally robbed of it. This hypothesis elegantly explains the location and the fragility of these ultra-diffuse galaxies. They are not cosmic rebels born different. They are survivors of a gravitational mugging, left drifting and weightless in the wake of a giant. The galaxy's pristine appearance became the next battleground. If tidal stripping was the culprit, the evidence should be carved across the sky. A violent gravitational mugging leaves scars. Astronomers scoured the deepest images of NGC 1052 DF2 and its sibling, searching for the telltale signs of a crime in progress. They looked for tidal tails, long, faint streams of stars being ripped away like cosmic cotton candy. They examined the galaxy's shapes, expecting to see the stretched, distorted forms of objects under immense strain. The initial observations were surprising. Both galaxies appeared remarkably symmetric and undisturbed. their starlight faded smoothly from the center outward in a classic, serene profile. They looked like calm, isolated islands, not survivors of a recent cataclysm. This pristine quality became the strongest argument against the stripping theory. How could something be violently robbed and show no signs of a struggle? It was as if a bank vault was found empty, but the door was still locked and the walls untouched. This visual evidence gave weight to the original, shocking idea that these were indeed born different galaxies that formed in a void without the dark matter seed. But science demands more than a single snapshot. The hunt for scars went deeper. Another team, using the ultra-sensitive dragonfly array again, peered even further into the faint outskirts of these ghostly objects. And there, in the most tenuous glow, they claimed to see something. Faint, asymmetric extensions, wisps of light that did not belong to the smooth galaxy profile. These could be the ghostly afterimage of tidal tails, the very streams of stolen stars predicted by the simulations. The problem was their extreme faintness, right at the limit of what telescopes could detect. One group's significant discovery was another group's questionable noise. The debate over these faint features mirrored the earlier debate over distance, a conflict over interpreting the dimmest whispers of light from the cosmos. This is science in its rawest form, a meticulous, contentious, and collaborative process of interrogation. The evidence remained tantalizingly ambiguous, a Rorschach test written in starlight where every observer saw a different story. But what if the crime scene was staged? The pristine shape and missing dark matter could point to a far stranger origin story, one where these ghosts were never complete to begin with. A radical alternative theory suggests these galaxies were not robbed but born different. They are cosmic orphans, assembled from the wreckage of a catastrophe they never witnessed. This idea is called the backsplash or failed galaxy model. Picture two massive spiral galaxies, each embedded in its own vast halo of dark matter on a collision course. They merge in a violent, chaotic dance, their dark matter halos swirling together. During this titanic collision, huge clouds of ordinary gas are not just squeezed, they are violently flung outward, ejected at tremendous speeds into the intergalactic void. This ejected gas, now far from the dark matter of its parent galaxies, eventually cools and begins to collapse under its own gravity. Within these isolated clouds, stars ignite. A new galaxy is born, but it is born from orphan material. It has the stars, the structure, the light of a galaxy, but it lacks the foundational dark matter seed that started it all. It is a galaxy built from the leftovers, a cosmic afterthought. This theory directly challenges the standard model of cosmology, where the story is always the same. First, dark matter condenses into invisible clumps, its gravity creating wells in the fabric of space. Then, ordinary gas drains into those wells, cools, and forms stars. The dark matter halo comes first, always. It is the seed, and the galaxy is the tree that grows from it. A galaxy without dark matter turns that sequence on its head. It suggests a galaxy can grow from a seed of pure gas, a possibility our current rulebook does not allow. If true, it means our universe has more than one way to build a city of stars, and we have only just begun to read the instructions. Our entire understanding of the cosmos rests on a single, elegant blueprint. Scientists call it the lambda cold dark matter model, or lambda CDM for short. This is not just a theory about galaxies, it is the operating manual for the universe. It describes everything from the Big Bang to the large-scale structure we see today, a cosmic web of galaxies strung along filaments of dark matter. In this model, dark matter is not just important, it is the lead actor. It is the cold, slow-moving particle that first clumped together after the birth of the universe. Its gravity created the initial wells, the cosmic potholes, into which ordinary gas later flowed. Stars ignited, galaxies assembled, and everything we see blossomed within these invisible scaffolds. The lambda CDM model has been spectacularly successful. It predicts the precise patterns in the cosmic microwave background, the distribution of galaxies across billions of light years, and the accelerating expansion of the universe driven by dark energy, the lambda in its name. It is the foundation of modern cosmology, and that is precisely why a galaxy with no dark matter is so profoundly disruptive. This is not a debate about a couple of strange objects in a distant cluster. This is a stress test for the foundational pillar of our cosmic rulebook. If galaxies can exist without dark matter, then the sequence of events in Lambda Citium is wrong. The scaffolding is not always necessary. The universe has a backdoor, a way to build structures we do not understand. Finding even one genuine counterexample forces scientists to ask a terrifying and exhilarating question. Is our elegant blueprint a complete picture, or are we missing entire chapters in the story of creation? The fate of two faint, ghostly galaxies now holds the weight of the universe's entire narrative. Perhaps the ghostly galaxies point to a flaw not in the universe, but in our understanding of gravity itself. For decades, a small but persistent group of physicists have championed a radical alternative to dark matter called modified Newtonian dynamics, or MN. Its premise is beautifully simple. What if there is no missing mass? What if instead our equations for gravity are subtly incomplete? The theory proposes that Isaac Newton's famous law, and even Einstein's refinements, break down in environments of extremely weak gravity, the kind found in the outer fringes of galaxies. In these quiet, low-acceleration realms, gravity becomes slightly stronger than predicted. This extra gravitational kick would explain why stars on the edges of spiral galaxies orbit so quickly without needing to invoke any invisible matter. For MN supporters, dark matter is an elaborate phantom, a story we invented to cover up a gap in our fundamental physics. The discovery of galaxies like NGC 1052 DF2 should have been a triumphant moment for MN. If gravity is simply stronger at low accelerations, then a galaxy with only visible matter should still behave according to MN's modified rules. But when the theorists crunched the numbers, they faced a shocking setback. According to MN's own predictions, even without dark matter, the stars in these ultra-diffuse galaxies should have been moving faster than what was observed. The galaxies were too slow, not just for dark matter, but for modified gravity as well. This created a profound and ironic twist. The very objects hailed as proof against dark matter also became a serious problem for its most prominent rival. They were cosmic outlaws, breaking the rules of both major theories. This layered the mystery with exquisite complexity. If the measurements held, it meant these ghostly galaxies were not evidence for one theory over the other. They were evidence against both. They pointed towards something entirely new, a phenomenon neither camp had anticipated. The puzzle was no longer a simple either-or choice. It had become a double-edged sword, cutting at the foundations of our understanding from two different directions. What do you do when the universe throws you a curveball that contradicts every rulebook you have? The ghostly galaxies refused to give up their secret easily. To settle the furious distance debate, astronomers needed a cosmic yardstick of impeccable precision. They turned the most famous telescope in history, the Hubble Space Telescope, toward these faint smudges with a single, focused mission: to find the tip of the red giant branch. This method sounds complex, but its logic is beautifully straightforward. Within any old population of stars, there exists a specific type of aging red giant that has reached a critical point in its life. At this moment, just before it ignites a shell of helium around its core, the star shines with a very specific, known intrinsic brightness. Think of it as a standard light bulb the universe installs in every galaxy. By finding these particular stars and measuring exactly how dim they appear from Earth, astronomers can calculate the distance with remarkable accuracy. It is like seeing identical lanterns on distant hillsides. The fainter the glow, the farther away the hill must be. For NGC 1052 DF2, finding these stars was a monumental task. The galaxy is so diffuse, its stars so sparse, that picking out individual red giants from the background noise was like trying to spot specific candles in a city viewed from an airplane at night. Hubble's sharp, unwavering gaze was the only tool capable of such a delicate measurement. Multiple independent teams painstakingly analyzed the Hubble data, filtering out foreground stars from our own Milky Way and isolating the true residents of the ghostly galaxy. After years of analysis, a consensus began to emerge from the stellar census. The distance measurements using the tip of the red giant branch method consistently pointed to a location about 65 million light-years away. This was the farther distance, the one that originally supported the shocking no dark matter conclusion. A closer distance would have resolved the mystery into ordinary physics, but the universe, it seemed, was insisting on being strange. With this more settled distance, the math became even more compelling. The galaxy's large physical size, combined with the languid motion of its star clusters, once again demanded a total mass that aligned almost perfectly with its visible stars alone. The dark matter was not just missing, its absence was being confirmed by the most trusted ruler in the cosmos. Yet, in science, a consensus is not the end of a story. It is the foundation for the next, even harder question. If the distance is truly settled and the ghost is real, then what catastrophic or bizarre process left it that way? Into this stalemate of starlight and statistics, a new judge has taken the bench, one with the power to see through the cosmic fog. The James Webb Space Telescope, humanity's most powerful eye on the universe, has turned its golden mirror toward the ghostly galaxies. Its mission is not to take sides, but to reveal the truth with a clarity we have never before possessed. While Hubble saw invisible light, Webb sees in infrared, a form of light that acts as a cosmic X-ray. It peers straight through veils of interstellar dust that can obscure and redden starlight, a key source of error in distance measurements. More importantly, its incredible resolution allows it to isolate individual stars in these ultra-diffuse galaxies with surgical precision, picking out the critical red giant branch stars from the background with undeniable certainty. This is the ultimate cosmic yardstick being applied with the finest tools ever built. Astronomers are not just re-measuring the distance, they are conducting a forensic examination of the galaxy's very population, its age, its history, written in the light of its oldest stars. The data from these observations is flowing down to Earth right now, terabytes of pristine information waiting to be decoded. Will it confirm the greater distance, solidifying the case for a true dark matter ghost? Or will it reveal a subtler truth, perhaps showing faint tidal features too delicate for Hubble to see, evidence of the long-ago gravitational theft? Webb acts as the final arbiter in this decade-long courtroom drama. Its verdict, etched in infrared photons, could either crown Lambda Citium by revealing the stripping scars, or it could plunge cosmology into a deeper mystery by presenting a pristine, undeniable anomaly. We are living in the moment between the closing arguments and the judge's decision, waiting for the universe to deliver its final word on the case of the missing ghost. The search did not end with those two ghostly whispers. If galaxies without dark matter are a real phenomenon, they cannot be solitary cosmic accidents. They must belong to a family. This realization has launched a new era of astronomical detective work, a systematic hunt for more members of this impossible class. Astronomers are now scouring the sky with powerful new surveys like the Dragonfly Wide Field Survey, specifically designed to find the faintest, most diffuse objects. They are no longer stumbling upon anomalies by chance. They are actively hunting for ghosts, knowing exactly what to look for. The goal is to build a census to move from anecdote to data. Have they found more candidates? The answer is a tantalizing maybe. A handful of other ultra-diffuse galaxies in different clusters and groups have shown similarly sluggish star motions in initial studies. Galaxies with names like AGC 1405 and NGC 1505 DF2 are now on the watch list, their properties suggesting they, too, might be missing their dark matter halos. But confirming each one requires the same painstaking process, measuring distances and weighing stellar motions, a task that consumes precious time on the world's largest telescopes. Each new candidate is a promise and a puzzle, another piece of evidence waiting to be verified. The ultimate power lies in statistics. Finding one or two strange galaxies could be explained by a rare and violent event like that dramatic tidal stripping. But if surveys reveal a whole population of them scattered across different environments, the implications are staggering. A population would mean this is not a fluke of destruction, but a legitimate path of creation. It would force us to accept that the universe has a recipe for building galaxies without its primary ingredient. This would be a genuine revolution in our understanding of cosmic structure. Conversely, if after exhaustive searches, DF2 and DF4 remain the only convincing examples, their story changes. They become fascinating oddballs, cosmic curiosities whose strange history we may never fully unravel, but they would not overturn the foundational rules. They would be the exceptions that prove the rule rather than the rule breakers that demand new laws. This is why every new candidate galaxy causes such a stir. It is not just another entry in a catalogue, it is a vote for or against a paradigm shift. This expanding search is doing more than just hunting for missing dark matter. It is fundamentally broadening our view of what a galaxy can be. For centuries, our galactic zoo was limited to what our telescopes could easily see, the bright spirals and ellipticals. Now, with sensitive instruments, we are discovering an entire hidden universe of faint, fragile structures. Ultra-diffuse galaxies, whether they contain dark matter or not, are rewriting the definition of a galaxy itself. They show us that collections of stars can exist in states of extreme fragility, vast yet nearly empty, challenging our ideas about how stars form and how structures survive in a dynamic cosmos. The hunt for the ghosts is in essence a census of the invisible and the improbable. It is reminding us that our maps of the universe are still incomplete, and that the most profound discoveries often begin with the faintest glimmer of light, a whisper from the dark asking us to reconsider everything we think we know. Behind every cosmic mystery are people driven by a relentless curiosity that borders on obsession. This is not a dry academic dispute, it is a human story of rivalry, passion, and the arduous pursuit of truth. On one side stands Pieter van Dokkum, the astronomer whose team first spotted the ghostly galaxies. For him, the initial discovery was a moment of pure shock, followed by a years-long campaign to defend it. His work is characterized by a quiet, meticulous patience, building custom telescopes like Dragonfly to see what others cannot, and then enduring the storm of skepticism that follows. He represents the archetype of the careful observer, convinced the universe has shown him something genuinely new and willing to stake his reputation on it. Across the debate are scientists like Ignacio Trujillo and others, whose role is equally vital. They are the rigorous interrogators. Their skepticism is not dismissal, it is a protective instinct for the integrity of the field. When they published papers challenging the distance measurement, they were doing exactly what science demands, stress testing an extraordinary claim with every tool available. Their driving question was not could we be wrong, but how could we be wrong, and it is that mindset that forces discoveries to prove their worth. The discourse played out in the pages of prestigious journals and in conference halls, sometimes with a palpable intensity. Published papers were not just exchanges of data, they were intellectual duels. A new analysis from Van Dokkum's team would be met within months with a detailed rebuttal pointing out potential flaws. The titles of these papers tell the story, from claims of a galaxy lacking dark matter to counterclaims of a distance miscalculation. In person, the debates were passionate. Scientists would gather after talks, arguing over faint smudges in Hubble images with the fervor of sports fans debating a controversial call. This friction is not a bug in the system, it is the feature. It is the sound of science working. No single person or team gets to declare a truth. The entire community must be convinced piece by painful piece. This process can be bruising for the individuals involved. Imagine dedicating years of your life to a finding, only to have colleagues you respect stand up and systematically pick it apart in front of your peers. Yet, this adversarial process is what separates a fleeting anomaly from a lasting revolution. It forges stronger evidence and clearer thinking. What fuels both sides is a shared, profound dedication to understanding the cosmos, a passion that overrides ego. Van Dockum and his critics are not enemies, they are collaborators in a high-stakes puzzle, even if their methods are oppositional. The skeptics are not trying to destroy our idea, they are trying to save cosmology from a potential dead end. If the galaxy is an illusion caused by a measurement error, then chasing its implications would lead the whole field astray. Their duty is to be the universe's devil's advocate. Conversely, Van Dockum's persistence comes from a belief that the most exciting moments in science happen when nature surprises us. He is driven by the possibility of seeing a crack in the foundation, a chance to glimpse a deeper layer of reality. This tension between conservative rigor and revolutionary openness is the engine of discovery. It ensures that when a consensus finally forms, whether it confirms the ghost or banishes it, it is built on a foundation that has been hammered, tested, and tempered by fire. The story of these galaxies is therefore a testament to human character, to the stubbornness and humility required to listen to the universe, especially when it whispers something we do not want to hear. These ghostly galaxies are not just cosmic curiosities, they are windows into the life cycles of all galaxies. Their very existence, whether born strange or made strange, forces us to rewrite chapters in the story of galactic evolution. If the tidal stripping theory is correct, then these fragile objects are teaching us about the silent, violent drama that unfolds in seemingly quiet corners of the universe. Galaxy groups are not serene retirement homes for aging stars, they are brutal arenas. The slow, gravitational mugging of a dwarf galaxy by a giant neighbor is a common but hidden process. We have likely been underestimating how efficiently these giants can strip away the identity of smaller companions, leaving behind only ethereal ghosts as evidence of the crime. These ultra-diffuse galaxies, then, become the fossil records of past interactions. They show us the end result of a process that shapes all galaxy clusters, a demonstration of how the cosmic environment sculpts and transforms its inhabitants over billions of years. They are the survivors, the ones that had just enough stellar density to hold on after losing their dark matter protection. Their presence tells us that galaxy evolution is not just about stars being born and dying within an isolated system. It is also about theft, loss, and identity erased by a more powerful neighbor. But if the alternative is true, if these galaxies truly formed without dark matter from the start, the implications are even more profound for our cosmic family tree. It means the universe has more than one recipe for building a galaxy. The standard model describes a single, dominant lineage where every galaxy, from the mightiest spiral to the tiniest dwarf, is born from a seed of dark matter. Finding a galaxy that bypasses this step is like discovering a complex animal that does not share our DNA, a life form built on entirely different principles. It suggests a parallel branch on the galactic evolutionary tree, a rare but legitimate path where clouds of pure gas, perhaps ejected from a galactic collision, can coalesce into a stable structure on their own. This would dramatically expand the diversity of what we consider a galaxy. It forces us to ask how many other strange forms are out there, hiding in plain sight because they do not fit our narrow expectations. These objects would not be the failed products of violence, but the successful products of an entirely different kind of genesis. Their quiet, diffuse lives would represent a unique evolutionary endpoint, one where a galaxy never develops the dense, rotating disks or bustling stellar nurseries we associate with galactic maturity. They would live and die as gentle, transparent wisps. Ultimately, whether they are stripped relics or born orphans, these galaxies expose the incredible diversity of galactic fates. They challenge the idea of a single, neat narrative for how a collection of stars comes to be and how it changes over time. They remind us that the cosmos is a laboratory of extreme experiments. Some galaxies, like our Milky Way, live robust lives within powerful dark matter halos, growing and evolving over eons. Others may have their foundational essence stolen from them, becoming fragile shadows of their former selves. And a select few, if the most radical interpretation holds, might skip the dark matter step entirely, embarking on a lonely, lightweight existence from their very first star. Each possibility paints a richer, more complex, and more violent portrait of the universe. These faint smudges of light are not merely missing a component, they are highlighting the gaps in our own story. They ask us to consider that for every majestic spiral we admire, there may be a dozen silent ghosts, each carrying a different truth about how the cosmos builds its cities and how, eventually, it takes them apart. The true weight of this mystery is not measured in solar masses, but in the assumptions it shatters. For centuries, science has progressed by a simple, powerful method. We observe the universe, we build a model that explains our observations, and we use that model to make predictions. The Lambda CDM model is the pinnacle of this process, a crowning achievement of modern cosmology that predicts the large-scale structure of everything we see. But what happens when a single, faint, contradictory data point refuses to fit? The case of the dark matter-free galaxy forces a profound and uncomfortable philosophical question. Are we discovering something new about the universe, or are we merely bumping against the limits of our own imagination? This is the challenge of the unknown unknown. We are adept at solving puzzles where we know the pieces are missing. Dark matter itself was an unknown that became a known unknown. We saw its gravitational shadow and gave it a name. But a galaxy like this suggests something else entirely, a gap in reality we did not even think to look for. It hints that our entire framework might be built inside a box, and we have just found a crack showing there is an outside. This is how scientific revolutions begin, not with a triumphant eureka, but with a persistent, nagging anomaly that refuses to go away. History is written by these cosmic rebels. Consider the shift from an Earth-centered to a Sun-centered universe. For generations, astronomers used elaborate models of epicycles to explain the peculiar retrograde motion of planets, clinging to the cherished belief that Earth was the immovable center. The data was forced to fit the assumption. It took the courage of Copernicus and later the telescope of Galileo to accept a simpler, more elegant truth that required a far more humbling place for humanity. The discovery of dark energy in the late 1990s is a more recent example. Astronomers measuring distant supernova expected to find the universe's expansion slowing down due to gravity. Instead, they found it was speeding up, driven by a mysterious repulsive force nobody had predicted. It was a complete shock that overturned a fundamental expectation and revealed that we understood only about 5% of the cosmos. The ghostly galaxy stands in this same revolutionary tradition. It is a data point that whispers our model, however elegant and successful, might be incomplete. It forces scientists to do the hardest thing imaginable, to question the very rules they have spent their careers proving. This is the essential, often painful, engine of progress. A scientist's greatest strength is not their knowledge, but their willingness to let that knowledge be wrong. The most cherished belief in cosmology is that dark matter is the indispensable seed for all structure. To entertain the idea that a galaxy could form without it is to hold that foundational belief up to the light and look for flaws. This process is not a sign of crisis, but of a healthy, living science. It is the sound of the universe talking back, reminding us that our maps are still rough sketches of a territory far stranger than we can conceive. The ultimate lesson of NGC 1052 DF2 may not be about dark matter at all, but about humility. It tells us that the cosmos reserves the right to surprise us, to present a puzzle where we do not even know what the picture is supposed to be. And in that unsettling uncertainty lies the thrilling possibility of discovering not just a new fact, but a whole new chapter in the story of everything. This ghostly galaxy is a crack in one pillar of our cosmic foundation, but the entire structure rests on two. For every 5 parts of the invisible dark matter that sculpts the universe, there are 7 parts of something even more mysterious, dark energy. Together, these two unknown entities make up 95% of everything that is. Dark matter pulls, its gravity assembling galaxies into a vast cosmic web. Dark energy pushes, a repulsive force causing the expansion of the universe to accelerate, tearing that web apart over cosmic time. Our standard model of cosmology is a precise, beautiful equation balancing these two opposing forces, the architect and the demolisher, across 14 billion years. But here is the unsettling thought. If we have misunderstood the architect, how can we trust our predictions about the demolisher? The properties of dark energy, its strength and constancy, are inferred from observing how the universe has expanded. We measure this using distant supernova and the cosmic microwave background, but these measurements all assume the standard role of dark matter in how structures form and evolve. Dark matter provides the gravitational counterweight against which dark energy's push is measured. If dark matter is not always the reliable, universal scaffold we believe it to be, if galaxies can form or be stripped in ways our models do not predict, then the entire historical reconstruction of the universe's expansion comes into question. The ripples from this one faint galaxy could travel all the way to the end of time. Imagine trying to predict the exact path of a balloon released in a storm, but you have miscalculated the weight of the balloon itself. Your prediction for where it will go and how fast will be fundamentally wrong. In the same way, if our accounting of dark matter's gravitational influence is flawed in certain environments, our measurement of dark energy's relentless push could be off. This is not a small correction. It strikes at the heart of cosmology's ultimate question: what is the fate of the cosmos? Will the expansion accelerate forever, leading to a cold, dark, and isolated big freeze? Could dark energy grow stronger, eventually overcoming even the forces that hold atoms together, resulting in a catastrophic big rip? Our answers depend entirely on the precise balance between the pull of dark matter and the push of dark energy. A single anomaly in a distant cluster of galaxies cannot change those answers by itself. But it acts as a warning light on the dashboard of our cosmic model. It tells us that a key variable in our most important equation might be more complex, more nuanced than we have assumed. If the ghostly galaxies are real and born different, they suggest the universe has wild cards, processes that do not follow the standard script. If they are stripped relics, they reveal a violence in galactic evolution that our smooth models may oversimplify. Either way, the implication is that our map of the cosmic forces, drawn from observations of billions of galaxies, might have subtle, systemic errors woven into its fabric. The search for the truth about these faint smudges of light is therefore about more than classifying oddballs. It is a stress test for our entire narrative of existence from the first second to the last. What we learn from the ghost could ultimately tell us whether the universe will fade quietly into darkness or tear itself apart in a final, spectacular flash. The most profound mysteries have a way of escaping the ivory tower and capturing the public's imagination. This story of the ghostly galaxy did just that, transforming from a dense academic paper into a global conversation. It spread across YouTube channels, science blogs, and social media platforms where creators used animations, analogies, and plain language to unpack the cosmic stakes for millions. This public engagement is not just a side effect of cool science, it is becoming a vital part of the discovery process itself. Consider the Galaxy Zoo project, where anyone with an internet connection can help astronomers by visually classifying galaxies from telescope images. This crowdsourced effort, fueled by human pattern recognition that still surpasses algorithms, has sorted through millions of galaxies, identifying rare and peculiar specimens that computers might have missed. It is entirely possible that the next great cosmic anomaly, the next galaxy that defies all expectations, will first be flagged not by a PhD in an observatory, but by a teacher, a student, or an enthusiast sitting at their kitchen table after dinner. This democratization of discovery changes our relationship with the cosmos. You are no longer just a passive observer of science, you can be an active participant in its unfolding story. So as this mystery hangs in the balance, waiting for the final verdict from telescopes like James Webb, where does your intuition lead you? Which explanation feels more compelling, the violent tale of a galaxy stripped of its dark matter by a cosmic giant, or the radical idea of an orphan galaxy born from pure gas, a cosmic rebel from the start? Your curiosity is not separate from the scientific journey, it is the very fuel that drives it forward. Every time someone shares a video, debates a theory online, or simply looks up at the night sky and wonders, they are adding to the collective human effort to understand our place in this vast, strange, and ghostly universe. The verdict on these cosmic ghosts will not come from a single judge, but from a jury of new telescopes about to open their eyes to the sky. While the James Webb Space Telescope offers a deep, forensic look, the next leap will come from telescopes built not for piercing stares but for panoramic views. We are entering an era of cosmic census, and the machines leading it have names like Vera C, Rubin and Nancy Grace Roman. The Vera C, Rubin Observatory, perched on a Chilean mountaintop, is not a traditional telescope. It is an unstoppable scanning engine. Every few nights, its enormous mirror and giant camera will capture the entire visible southern sky, a task it will repeat for an entire decade. This relentless survey will create the deepest, widest movie of the universe ever made. It will not just look at a few ghostly candidates, it will systematically map billions of galaxies, measuring their shapes, speeds, and positions. Within this ocean of data, the hunt for ultra-diffuse galaxies transforms from a painstaking search into a statistical certainty. Rubin's algorithms will sift the sky, automatically flagging thousands of faint, wispy objects that match the profile of DF2. For the first time, astronomers will have a true population to study. They will be able to answer the critical question, are these ghosts loners or are they everywhere? The Nancy Grace Roman Space Telescope, NAS, a next great observatory, will join this effort with a superpower. It can peer through the dusty veils of the universe with its infrared vision, while also covering a field of view 100 times larger than Hubble's. Roman will conduct its own vast surveys, finding the faintest structures in the most distant clusters. Together, these observatories will do more than just count ghosts, they will place them in their cosmic context. Scientists will see with crystal clarity if these galaxies are always found near massive neighbors, their positions betraying a history of tidal stripping. Or they might find them floating in isolated voids far from any gravitational bully, which would be the strongest evidence yet for a truly different birth. The data will be overwhelming and transformative. Imagine having a map of a single strange island versus having a complete atlas of an entire archipelago. The atlas reveals patterns. It shows if the islands are linked by submerged ridges or scattered randomly by ancient cataclysms. Within the next decade, we will have that atlas for the faintest galaxies in the universe. Each new candidate will be a data point, and dozens of points will draw a line toward a definitive answer. This is the power of statistics. It moves us beyond arguing over individual anomalies and into the realm of understanding a phenomenon's true place in the cosmic order. The golden age for solving this riddle is not a distant dream. It is being built right now in clean rooms and on mountaintops, waiting for the moment the dome opens and the sky pours in. The evidence has been gathered, the arguments have been made, and the universe has yet to deliver a final verdict. So where does this cosmic detective story stand today? The latest research paints a picture of a mystery still very much in motion, with compelling evidence on all sides. On one hand, the most precise distance measurements from Hubble's red giant branch stars consistently place the galaxy far away, a finding that solidifies the original shocking claim of missing mass. The existence of a second, similar galaxy in the same neighborhood strengthens the case that this is not a one-time fluke, but a potential pattern. Yet the counter-arguments remain powerful. Some analyses of the deepest images still suggest those faint, ghostly tidal tails, the signature of a violent gravitational stripping. The pristine shape of the galaxies argues against a recent mugging, but perhaps the theft happened so long ago that the scars have almost faded from view. This leaves us with three distinct paths forward, each with profound implications. The first possibility is the most revolutionary, that these are indeed strange but real galaxies born without dark matter, challenging the very sequence of cosmic structure. The second is more conservative but no less dramatic, that they are normal galaxies brutally robbed of their dark matter halos, teaching us about the hidden violence within galaxy clusters. The third, and always present in science, is the humbling chance that there is a fundamental error in our observations or a subtle flaw in our theoretical assumptions that we have not yet uncovered. The scales have not decisively tipped. For every point there is a counterpoint. This is not a sign of failure, but of a mystery operating at the very edge of our understanding. The ghost has been seen, but its true nature remains just out of reach, a faint whisper in the data that refuses to be silenced. Ultimately, the true value of this ghostly galaxy lies not in which theory it proves, but in the sheer fact of its discovery. Whether NGC 1052 DF2 is a cosmic rebel born without dark matter or a stripped relic of a gravitational crime, its existence has already forced a revolution in how we look at the universe. It pushed our telescopes to their absolute limits, demanding new ways to see the faintest whispers of light. It stretched our theoretical models to the breaking point, forcing brilliant minds to defend, attack, and reimagine the cosmic rulebook. This is science operating at its absolute best, not when everything fits neatly into place, but when something stubbornly refuses to fit. History tells us that the greatest leaps in understanding never come from confirming what we already know. They come from the anomalies, the cosmic outliers, the data points that whisper, "You are missing something." The faint smudge of this galaxy is a perfect example. It is a question mark written in starlight, and the decade-long struggle to answer it has sharpened our tools, clarified our thinking, and revealed hidden complexities in the life of galaxies we thought we understood. So the next time you find yourself looking up at a clear night sky, remember this: that vast darkness is not empty. It is filled with questions. For every bright, familiar star, there may be 100 ghostly mysteries waiting to be found, each one holding the potential to overturn a cherished truth. The universe is not a static museum of facts we have already catalogued. It is a living, breathing puzzle, forever stranger and more wonderful than we can possibly imagine. Our journey is not about finding final answers, but about learning to ask better questions, stay curious,